Hello there, I'm Thomas Hodges, a German-American pilot flying the Boeing 787-900 night flight. We're gonna be overflying Zurich, Switzerland, Germany, then coming back to Zurich International Airport, runway 14 for an ILS localizer. Landing soon, I'm in the cockpit for the pre-takeoff preparation of the quality wings, Boeing 787-900 and Microsoft Flight Simulator. Right, I'm gonna start showing you the cockpit instruments that displays the functions of the Boeing 787-900. That aircraft. I'm going to start with the primary flight display that displays the airspeed indicator, the airspeed selected from the autopilot flight director system panel, the ground speed, the radio altitude above the ground level, the barometric altitude above the sea level, the target altitude selected from the autopilot flight director system panel, the barometric pressure of the right atmosphere, the other indicator with the pitch ladder in degrees and the bank angle in degrees. Also we have also the indicator with the pitch ladder decrease and the back angle indicates the ILS localizer, the horizontal localizer, and the vertical glide slope. That display the ILS localizer information for the runway we have selected for takeoff and for landing. It receives the ILS localizer frequency from the runway transmitters through its receivers and displays the ILS localizer, horizontal and vertical guidance. We have also the flight director crossbars for manual guidance of the aircraft and the autopilot crossbars for automatic guidance of the aircraft. We have also the angle of attack of the aircraft as it flies and the flight mode on 0 with the autopilot and the autothrottle meter and vertical navigation modes. We have also the navigation display. The navigation display that displays the inertial reference position, the GPS position of the aircraft, the terrain and weather reflections from the weather radar. You can see also the horizontal and the vertical profile of the aircraft flight plan. I have created. I'm gonna create right now using the flight management computer, so I can show you here. You see the flight management computer. I will input all the data we need for this flight. So I will initialize the route. So come over here in the control contract. So I will insert all the data for this flight. As you can see over here, we have the index. We can select either item, position, performance, takeoff, approach, announce status, navigation data, flight plan, load plan, save plan, save flight plan. So the ident is here. Position is here, reference airport. We will select the Lszh, the performance. So we have the route over here. So the position Lszh, we're gonna have the reference position, GPS over here, coordinates, as you can see from the GPS receiver. The index, we have the route here, origin Lszh, Zurich International Airport, Lszh, origin and destination over here. Runway 14, we select the departing runway. Over here, departure arrivals. We select again 14 Trans-Zui to Alpha. Arrivals over here, ILS 14, ILS localizer approach over here, as you can see. So we select over here trans, the stars, standard terminal arrival waypoints, fixes for the terminal arrival approach, Negria. So we have the route completed like this, and you can see we have only one route discontinuity here. we cancel the discontinuity, and we have to insert also the flight level we're gonna be flying. We have the performance here. So the flight level is gonna be at 35,000. So we select the gross weight, fuel on board, zero fuel weight, reserves, the cost index 100%, the minimum fuel temperature, and the cruising center of gravity over here. It's gonna be 28%. So we're gonna select the flaps here, 15 degrees of flaps, center of gravity 23%, and the horizontal tail trim stabilizer. So we have the V1, V-rotate, and V2, the gross weight with the takeoff weight, runway position, so over here we execute that, the legs from takeoff, 250 knots, 1900 feet above the ground level, leader set, Zui 250, 6000 alpha, Negra Mativ, Almeki, Zui, Zurich ZH701, TRA, C1 14, CI 14, Osnem, runway 14. So this is the complete route here, with the flaps for takeoff here, the center of gravity, and the takeoff. So this is the complete flight plan using the flight management computer. I input all the data for this flight, the takeoff gross weight, that includes the empty weight plus passenger plus cargo plus the fuel on board. As you can see, the route, the legs, fixes, alternate, progress, communications, hold, navigation, radio. So we have the legs here. So you can see also here we have the flight plan displayed in the navigation display. You can see the horizontal and the vertical profile. We're going to be flying flight level 250 or higher, below 1,000 feet, below 10,000, above 10,000, I believe. Flight level 110, 120. You can see also the runway we are located, this side here, this side, here in the display, the terrain is below and in front of you. So now we have all the navigation data we need for this flight, completed flight plan. So I created a flight plan using the flight management computer. We have the navigation display. The navigation display, so the display that the horizontal vertical navigation profile of the aircraft, the terrain map, and the weather and terrain reflections from the weather radar. You can see the red, green, and yellow reflections from the terrain around you. We have the magnetic north pole and north pole and magnetic variation depending on where we are in the world. We have the display of the airports in the terrain map, and also the runways we're gonna use for takeoff and for landing. So we have the Zurich International Airport Lszh runway 14 for an ILS localizer takeoff and landing. We're gonna use the same airport, the Lszh Zurich International Airport runway 14. So I created the flight plan. You can see displaying the primary flight display, both horizontal and vertical. So if I connect the autopilot flight director system panel in flight, like above 400 feet above the ground level. After takeoff, using the L-navigation, now it's gonna follow the horizontal and the vertical profile of the flight plan, or the route, or the flight path course, as you like. I have created right now. So you can see also. So we have the also the display of the workstations, the ADFs, the NDBs, the waypoints. The waypoints, which are horizontal and vertical navigation fixes, the aircraft will have to transverse through during its flight. As it follows its flight plan, we have selected some waypoints for that. We have also we have also the display of other aircraft using the transponder and the DSP and ADC transmitter receiver that transmits our frequencies to other aircraft and the air traffic controls, and also receives from the other aircraft and displays. We can calculate the distance the other aircraft are located using the frequency, radio frequency receiver. The altitude difference, the distance, the altitude difference from our aircraft, if they are higher or lower, how many feet above or below, whether they climb or they descend with respect to our aircraft, how fast they are approaching or are moving away from us. So they will give us the TCAS system is going to give us a warning. The traffic collision advisory system is going to give us a warning if we have an incoming aircraft close to us, like less than 3 nautical miles away. So we have also in order to create the flight plan, I insert all the data of the aircraft. The takeoff gross weight, that includes the empty weight plus the passenger plus the cargo plus the fuel on board, where the cargo and the fuel are shown the left and the right wing, the fuel and the center tank, where the cargo and the fuselage. It is going to calculate the center of gravity automatically of the aircraft, and it's going to give us also the aerodynamic chord position of the aircraft, the Mach 23% of the Mach, and also the horizontal trim stabilizer for takeoff is going to be like 4.25 degrees for this flight, using 15 degrees of flaps. So as I told you, it's calculating the takeoff gross weight, that includes the empty weight plus the cargo plus the fuel on board plus the passenger, the fuel that includes the trip fuel, the reserve fuel, and the tax fuel, where the fuel is stored in the left and right wing tank, in the center tank. As it flies, it burns fuel, so it saves the center of gravity in flight, so it needs to recalculate everything. The mean aerodynamic core position and the horizontal trim stabilizer is going to be trimmed automatically during the whole flight, from takeoff, climb, cruise, descent, approach, and landing, using the auto trim function of the autopilot and flight director system panel and the auto throttle. And we can also trim it manually anytime we need, or if you like, using the horizontal trim stabilizer trim switch over here. So you can see this switch is the horizontal trim stabilizer. You can trim the horizontal tail of the aircraft. Over here, trim up and trim down. So I will start showing you the instrument, the explanation of the trim down and trim up like this. Nose up, nose down. We have the alternate also over here, alternate pitch trim. You can see nose down, nose up. Also the parking brakes besides that. And also we have these red carded switches here. If you have a failure of the auto trim, you can see auto stabilizer cutout switch. So you open from normal to cut off the stabilizer. So if you have a failure of the L2 and R2 hydraulic systems, it's gonna have a failure also of the auto trim from the autopilot and the auto throttle and the flight director. So you will need to come down here, disconnect. This is for all Boeing aircraft, as far as I know, the 737, 747, 757, 767, 777, 787. disconnect this from normal to cut off and use only the horizontal trim stabilizer over here, the manual input. So you will be flying in direct mode, I believe. Since this is a fly-by-wire aircraft, it has the normal mode with the auto trim and the protections, and a direct mode if you have a failure of the hydraulics. So you can see this is the horizontal trim. This is the horizontal tail plane. The horizontal tail you need to trim up or trim down during the flight. You can use also the elevator here of the horizontal tail, which is only a small section, using the side stick or the yoke of the aircraft like this. Descend and climb, as you can see. So you can climb like this and you can descend like this. Also use the rudder to make turns and the barn rolls, using the ailerons and the spoilers. So I'm gonna show you, I was talking about the horizontal trim stabilizer. So I use the runway, the takeoff gross weight, the minor dynamic chord position, the Mach 23% of the forward wings aerodynamic chord position is the position with the maximum aerodynamic lift occurs in the forward wings. It's also the position where the stall, the airflow of the air mass will become detached in the forward wings for a given angle of attack and airspeed in flight. So we need to monitor the stall speed over here in the primary flight display when we fly, and avoid it all the time, because it's gonna make the aircraft start falling. So we're gonna have is the position also the minor dynamic position. We calculate the center of gravity and the horizontal trim stabilizer over here. So I'm gonna talk to you about aeronautical and aerospace engineering and some Newton's physics and Bernoulli theory of fluids. So we have the forward wings. You can see the surface area of the wings holds the weight of the aircraft as the aircraft is flying. We have the thrust from the engine to move it forward, from the engines, the turbofan towards the engines. We have also the ailerons and the spoilers, the flight control surfaces to change the airflow as we fly. So you can see we have the minor dynamic core position is about here, 33% of the Mach is where the maximum dynamic lift occurs in the forward wings. Is the position where the stall will begin, the top surface, for given airspeed and angle of attack. So we need to avoid the stall speed. Is the position where we calculate the center of gravity, pretty much about here. We have the vertical axis, the longitudinal axis from nose to tail, to calculate also the horizontal tail trim and the vertical tail, the rudder position in flight, so we can make turns, for instance. Also the ailerons and spoilers. So you can see also the top surface. You can see maybe the bottom surface of the wings is more flat, so as the aircraft flies, the airflow is moving much slower below the wings, which pressurizes the aircraft weight up into the air. And also you can see the top surface of the wings is more curved, so it creates so the airflow is moving much faster above the wings, which makes which creates lower pressure above the wings, which sucks the aircraft up into the air. So this is the differential pressure from Bernoulli theory. Also Newton's physics, aeronautical and aerospace engineering. You need to know some principle for flying. So we're gonna have also inside the cockpit. I'm gonna start showing now the flight controls. The flight controls of the Boeing 787. How I use the side stick to control the flight controls of the Boeing 787. I have the load the stream 3D to control the vertical, the horizontal tail using the control column for climb and descent, and also the control wheel of the yoke to make the bungles left and right, using the ailerons and the spoilers in the left and the right way. We have also the vertical tail the rudder, using the rudder pedals to make yawing turns. We have also the nozzle steering in the ground, and the parking and the toe brakes from the rudder pedals. Also, the tiller is interconnected in the ground until somewhere speed like 70 knots. So you're gonna see also that. We have also the flaps and the slats lever, the speed brakes, the horizontal trim stabilizer, and the thrust levers are connected in the side stick. So we'll start showing now the side stick of the Boeing 787-900. Then I will come to the rest of the aircraft systems. So you can see here the side stick. Hope you have a nice view like this. You can see I can climb and descend like this using the control column, the vertical column of the yoke. I can use also ailerons and spoilers right and left, or the rudder pedals. If I want, I can use only one at a time. I can use them all together for a coordinated flight. All flight controls, making left and right turns, and also climb and descend if I need. So you can see the side stick deflection is proportional to the yoke deflection. You can see also the captain and the first officer are moving together in flight. They are interconnected unless we have some failure of the flight controls. They're not like in the Airbus aircraft where you have a side stick priority button. So you can see here, I will show you also now the outside view of the Boeing 787 flight controls, the inside and the outside view of using the side stick of the Lszh Extreme 3D. So I forgot also to show you that view over here. Yeah, I will show you first this view. So I hope you also like this view over here of the flight controls. So we have also that view. So you can make turns to the left, turns to the right, climb and descend like this. So climb, descend, make turns left and right using the rudder pedals, and also the thrust levers here. You can see I can actuate the thrust, move the thrust levers forward and aft over here. So I can control the thrust produced by the engines. You can see the left and right engine indication here. I will explain in a couple of minutes. Increase when we use when we move the thrust levers. We have also the outside view of the flight controls of the Boeing 787. So you have already see. I can use like this. So you can see again, climb, descend, make turns, turns left and turns right. Over here also the rudder pedals, left and right. So this is most of the flight controls until now. Climb, descent, control yoke, rudder pedals. We have also the nozzle steering. I forgot to mention the horizontal trim stabilizer over here. Also it's part of the flight control system. You can see the horizontal trim stabilizer here, the flaps position here. So we have also the flaps are now full extend, retract and extend again. Over here the speed brakes, retract and extend. So you see the speed brakes like this. You can see the speed brakes movement. So we have also, I will show you all the thrust levers, the autopilot flight director system panel, the displays over here. I'm gonna change some information. So using all this data in the flight management computer, we calculated the takeoff speed. We have the runway length, the runway slope, the wind direction and speed, the barometric altitude, the barometric pressure, the flaps for takeoff, the takeoff cross weight, the mean aerodynamic core position, the center of gravity, and the horizontal trim stabilizer. This is gonna give us for the runway conditions I told you, if it is ice, dry or wet, the barometric pressure, temperature, and wind direction. Is gonna give us the takeoff speeds V1, V0, and V2, which is the climb speed. Initial climb speed. We're gonna have to pitch up the aircraft like 9 degrees or less for takeoff to avoid a tail strike. We have also the V2 plus 15 knots, the initial 15 knots, the initial glide speed for this flap setting. We're gonna have then also in the navigation display the flight plan. Using the flight management computer I already created, I insert the seats, the other instrument, departure waypoints and fixes that include horizontal and vertical navigation fixes for the initial climb and departure of the aircraft, and altitude and airspeed constraints, the top of flight, the cruise like 35, 36, 27, 28, 29, 32,000 feet above the sea level. And then we have determined waypoints and fixes to cross through. Then the descent, we're gonna initialize the descent. We're gonna have the descent to like 7,000, 6,000 feet above the sea level. The approach altitude. So we're gonna initiate the long final and the short final approach and landing. So we're gonna have to cross the stars at our terminal arrival and startup terminal arrival waypoints and fixes that include horizontal and vertical navigation fixes for the terminal arrival to the airport, the Zurich International Airport runway 14. So we're gonna be aligned with the runway heading, the magnetic North Pole heading. I'm gonna use not the geographic North Pole heading. So we're gonna have the Lszh localizer. We're gonna tune the Lszh localizer automatically using the flight management computer. The frequency is gonna be received from the aircraft onboard sensors, which are transmitted from the runway antennas, and this is gonna help us align with the runway, the horizontal localizer and the vertical glide slope, the horizontal and the vertical path of the aircraft for approach and landing. So we're gonna have the flaps and the airspeed again set for landing. We're gonna use touchdown vertical rate of descent like 500 feet per minute or less, and a pitch altitude again of less than 9 degrees for the touchdown. So we're gonna have a complete flight plan of flight path or route for this flight. I'm gonna show you now the autopilot flight director system panel. I'm gonna change some information over here. The autopilot flight director system panel. So we have the autopilot over here. Engage and disengage switch over here. You can see pull out and disengage. We have the LNAV and the VNAV. So this maybe is gonna give us a better some kind of information pops up in the display. FMC Jerset heading. So you can see FMC Jerset heading. I don't know why it shows that. We have the auto throttle left and right. We can disarm the flight director. This is the flight director. We cannot rearm the autopilot or its modes unless we have the flight director on. So we turn off the LNAV. We can use flight level change, auto throttle climb continues. As I told you, autopilot disengage. So we're gonna use the airspeed like this. I'm gonna set the airspeed, indicated airspeed or Mach. Bank angle set to auto. Heading, we're gonna set the magnetic north pole heading again. 136 degrees over here. The altitude again. I'll set it. Vertical speed. So we can set the vertical speed like minus 2,500-3,000 feet per minute. Zeros and plus. You can see the plus sign now over here. So usually how fast I climb, like 3,500 feet per minute or more. So you're gonna see now all this information. It will show up over here in the head-up display. You can see LNAV, vertical speed, target airspeed, target altitude. Also in the primary flight display, you can see the airspeed indicated, airspeed selected from the autopilot flight director system panel, 253 knots. Target altitude 25,300 versus our altitude right now 1,430 feet above sea level. You can see the HSI, horizontal situation indicator, with the integrated display of the flight plan. Again, from takeoff, climb, over here cruise, then turn, descent, approach and landing. We have it also here, from takeoff this way, the runway, climb, cruise, descent, approach and landing over here. Also the vertical flight path. So we'll talk to you now about that. You can see the display, the altitude indicator, pitch ladder in degrees, 2.5, 5, 7.5, 10 degrees, plus or minus this climb or descent. We have also the vertical rate of climb and descent of the aircraft, 100,000 feet per minute. Or you can also use the steepness of the trigonometric angles. Over here, the flight path angle mode over here from the autopilot flight director system panel. So we have the radio altitude above the ground level, the barometric pressure of the outside atmosphere, flight director, LNAV, VNAV. So I'm gonna show you now the rest of the aircraft systems, the Boeing 787-900. I'll continue now over here with the navigation display. I will show you the navigation display data. You can see the terrain around you with yellow, green, yellow and also red, the terrain levels. If you look further away, you will see again some red over here, maybe some green, some lakes, maybe. Also the flight level we have to fly over here. You will see the cruise, the top of climb, then the descent over here. The flight altitude set. So this is the vertical profile and the horizontal over here. More close up view. You can see also the runway we have over here, runway 14, the heading and the taxiway in the other runway 16. You can see better view of the mountains. We are right now on the ground, as you can see the aircraft. Then we're gonna be flying. You can see how far above the ground we have some terrain in front of us when we fly. We have the terrain avoidance, other aircraft also, the LNAV. So the plan display also here. So we have a different mode here, display only the plan, and some airports if you like. So you can see the complete plan from takeoff over here, climb, cruise through this waypoint, then return, descent, approach and landing. You can see the runway heading and the aircraft where it's located right now, how far away from the runway we are. You can see also some other sub modes over here. So this is a nice view of the navigation display. I will show you also the engines indications. I'll show you the autopilot flight director system panel, the thrust levers. So we have a few more subsystems here. We have, as I told you, the flaps and the horizontal trim stabilizer, the rudder trim. Over here the landing gear extender retract, the alternate gear, the standby instrument display. We have alternate gear, lock override over here, auto brake, full landing, disarm and reject takeoff. Here also you can see in the display we have the gross weight for takeoff, total fuel on board, and the fuel temperature and the saturated temperature. So we have a few more instruments to look at. The thrust levers, you can see over here the left and the right engine, thrust lever, left and right, thrust reverses, takeoff, go around, auto throttle disconnect over here, so you press this, you disconnect the auto throttle. So I told you the flaps position in degrees, 25, 30, 20, 15, 10, 5, 1. Decrease the fuel flow per inch per 1000 kilograms, 1000 pounds. You can also close the fuel flow for the left and right engine. The fire extinguishers for the left and the right engine, which closes all the fuel flow. The transporter, the radio and communication panel here of the aircraft, and the rudder trim also. So gonna go over the overhead panel then after completing this section. I will start the electric system here, the APU, the primary flight control computers, the air data computers, flight control surfaces. So we have the air data computer, heading reference, IRS and SR reference system, GPS receivers, laser gyroscopes, pitot tube and pitot, dynamic and pitot dynamic, and also static, pitot static. So we have the airspeed and the altitude difference as we fly, increase and decrease, and also climb or descent rate, also radio altitude, magnetic north pole, geographic north pole, laser gyroscopes, the altitude of the aircraft, all these airspeed, all this navigation data, airspeed, altitude, angle of attack of the aircraft as it flies, GPS, also terrain maps and magnetic and geographic north pole. So all these are displayed from this data computer. We have also the flight control computers, the electric system. Also you have to start the engines in a couple of minutes. I will make an engine start demonstration first. I will show you the thrust reversers here. I will pull up. So we have the speed brakes retracted. If I pull up the thrust reverse over here, it will extend the speed brakes, and will, so the reverse is engaged here in the left and right engine with green color. So you can see reverse. We can close it, turn off the thrust reverse. So this is how it arms, like this in touchdown. Also and it disarms by moving forward the reversers. So you look out here in the engines, you see the information of the engines. We have the N1, which is the low speed starter, low pressure compressor and turbine of the turbofan, which is engine 21%, the takeoff limit 100.4. So this is the low speed starter, low pressure compressor and turbine of the turbofan, which is engine. We have also the pressurization here. I need to show you that. I will turn in the manual mode over here. It will give us some display of the cabin pressurization, which admits pressurizer from the engines over here. So we have more information now. So the N1, green, red, and yellow limits. Also exhaust gas temperature with limits. And 2, which is the high-speed starters of the high-pressure compression tube, one of the turbo fan engine, the left and the right engine. The fuel flow parameter per 1000 kilograms, 1000 pounds, oil pressure, oil temperature, oil quantity, and the vibration of the N2 stage of the engine. We have also the bleeder from the 5th and 9th stage of the engine supply, the cabin pressurization, we can engine the ice, air conditioning, ventilation, and hydraulic fluid tanks pressurization. So we have the cabin rate, cabin altitude, the rate of climb and descent, differential pressure, and landing altitude. So it will reach a differential pressure of like 7.8 maximum, with like maybe I don't know 8,000 or more feet, maybe higher of cabin altitude. So we're gonna see that later if we need in flight. So I'm gonna show you now also the rest of the functions of the instruments. So I'll explain you a little bit about the engines. We have the GNX engines installed in our Boeing 787-900 aircraft. One in the left wing, one in the right wing. First symmetrical thrust and redundancy. One produce a lot of thrust and that engine. Also contains a gearbox with the FADEX. The FADEX are the full authority. These electronic control computers. One installed per engine gearbox controls, displays, and monitors all the engine data you see in the upper and lower ACAS. Engine indication and crawler system display, automatic function display, like the N1, which is the low speed standard low pressure compression tube, and the 1, 2, which is the engine, which is gas temperature per engine. The N2, which is the high speed the high pressure compression tube, and the turbo 100, which is the engine. The fuel flow per 1,000 kilograms, 1,000 pounds, so the pressure, oil temperature, quantity, and the vibration of the N2 stage of the engine. Also controls and monitors the engine start, engine shutdown, engine failures, fuel metering unit, fuel flow per engine, per hour, oil heat exchange sensors, fuel heat exchange sensors. We need to heat the fuel on board the aircraft when we fly to avoid freezing. So it has the recirculation system to the engines automatically, which ducts heat from the engines into the fuel to heat the fuel and cool down some engine components. Also is doing the same with the lubricants in the oil. So we have also the pressure inside the engine. We have an overpressure or an underpressure. The FADEX, the full authorities electronic control computers, can control by opening the outflow valves of the 5th and 9th stage of the starters into higher or lower position to relieve or increase the pressure. Also, as we fly the aircraft, like when we take off from the sea level and we climb up like all the way up like 20, 30 or 40,000 feet above the sea level, like 9,000, 10,000, 11,000, 12,000 meters above the sea level. As we climb higher and higher, the pressure of the air, the temperature, the pressure of the air density, and the oxygen level are becoming less than that of the sea, less than half than that of the sea level. Also the aircraft, also the temperature of the air is becoming freezing, like minus 30, minus 40, minus 50, minus 60 degrees Celsius. Also the aircraft is going to be flying with an airspeed rate like 2 or 3 times faster than that of the sea level. So we have a higher intake of air mass from the front fan of the jet engines for compression and fuel mixture. So the vice versa is happening when we descend from the cruise level back to the sea level. So every second we need to adjust automatically the fuel mixture. And this is done using the FADEX, the full authorities electronic control computers. So it's a good thing to have the FADEX installed into your aircraft. Also the FADEX control, as I told you, the outflow air from the 5th and the 9th stage, and from the bypass air from the fan stage. So it admits pressurizer into the hydraulic fluid tanks. For hydraulic fluid, all these flight controls you see need hydraulic fluid, and receive pressurizer from the engines when they work. So you see all the flight controls here moving, like the wings, the elevator, the tail, all need hydraulic pressure. Also the landing gear extender retract here. the parking brake, the normal brakes, the thrust reversers from the engines, the flaps and slats, the speed brakes, horizontal tail, aileron, spoilers, rudder, all need hydraulic pressure from the engines, or the APU as a backup. So we have the APU also to start the engines. A smaller turbine is going to give us a pressurizer and electric power to start the engines. I'm going to show you right now the process, so we have a few more minutes. Also, the pressurizer from the engines is used for cabin pressurization with an engine idealizer, air conditioning and ventilation, and hydraulic fluid pressurization. So we need to start the APU right now. We have the electric panel, left and right IDC, the great drive generator, has the 200 volts, 400 Hz frequency. Also the battery, 31 volts. The APU generator here. So we have the primary flight control computers in the auto position, air data computer, flight control surfaces, some other systems, safety doors here, battery, window heat here, rammer turbine, hydraulic fluid here. We can turn off the primary and the demand of the left and right engine driving. We have the electric C1 and C2 also. So if you look up here, we can turn on again like this, the primary, the demand and the primary. So we have hydraulic fluid pressure. We have also the lighting system and the windshield wipers down here. We have the wing and exit guys here on an auto. We have the fire extinguishers for the APU and the cargo compartment. We have electronic engine control for the engines, the C mode with the auto start here. You can start the engine later. We have the fuel jettison. We can dump some fuel in flight if we arm this and select the nozzle. We have the left and right wing fuel tank, the fuel booster pumps over here, turn on and off. The sender tanks also. The crossfeed valve can feed either engine with either pump or either tank, or balance the fuel. We have also the balance if we need to balance down here. So we turn off this. We don't need the crossfeed right now. So we have also here the cabin pressurization. In the manual mode, we use the alpha valves, climate ascent, select landing altitude. Also the bleeder from the engines supplies the air conditioning and ventilation of the aircraft. So now we go into the last system before going into the engine start demonstration. The systems here. So everything you see over here in the overhead panel, all the formats, the diagrams, you will see them in the digital format display over here. So we have the hydraulic quantity, APU, oxygen and liquid cooling, the electric, left and right engine, IDG, APU, Lszh, main battery and APU battery. You can see how many volts, the contactors, the drive are connected here, the left and right engine. The hydraulics, where the hydraulic fluid goes, how much hydraulic quantity you have in the left and right engine, C1, C2 electric, set of valves, 5000 psi, it's left, right and center. So we have the fuel on board here, left and right wing fuel tank, center tank. The crossfeed valve is off, but if we turn it on, can feed either engine with other pump or either tank. The non-hard pressure fuel valves are open and feed both engines are running. Total fuel on board, how much fuel you have in each tank. The APU is fed from the left wing using the DC motor. So we have also the minimum fuel temperature below which the fuel will freeze, -37. We use the recirculation to the engine to heat the fuel, as I told you. So this is the ventilation and air conditioning pressurizer from the engines or the APU. The doors are closed, the cabin can be pressurized. The landing gear, you can see the pressure of the tires and temperature of the brakes, also the nose wheel. The flight controls here. So we have the flight controls, left and right. Again, so you see again all the flight controls moving accordingly over here. You can see the tail also, the rudder. So we have the last thing, the FS display, the maintenance over here. circuit breakers, also digital maintenance. So we have also the checklist, like in the Boeing 777, research normal menu, what to do, its items before start, takeoff, after takeoff, descent, approach, landing over here. So this is the last thing. We're gonna start the engines right now. So it's gonna take us like a couple of minutes to start the engines, and then we go in the complete flight from takeoff, climb, cruise, descent, approach, landing. So stay until the end part of the video. So we need to over here landing lights on. So we're gonna use the outflow valves over here off. Those off, you will see the engines are off. Some systems are popping up with yellow, with amber color axis. So we have the right and the left engine over here slowing down, so we need to start the engines very quickly over here. Go in the overhead engine, auto start both left and right engine. So this admits pressurizer from the APU. It's gonna initiate the pressurization of the engine starter right now. So we have enough pressurize there, as you can see. So we need to start the fuel flow like this, left and right fuel flow very quickly. So we have over here the auto start is kicking in, as you can see. We have the auto start now of the engines. So you can see here the engines roaring. The auto start is kicking in. So all the systems now are running, and we're gonna have with green over here the running engines. As you can see, both engines are running. So we can go now for takeoff. Only the flaps need to set. So we're ready now to taxi for takeoff. Advance the thrust levers, parking brakes off. So the runway is empty. We take the clearance from the air traffic control over here for takeoff. Align with the runway center line here. So we advance the thrust levers to the takeoff go around position, and we go. So we have over here V1, we rotate, rotation speed, and we go. So landing gear up, maximum takeoff thrust. So keep climbing, as you can see. We have all the indications here. The airspeed 180 knots, so the stall speed, the pitch altitude 17 degrees. We are 4,700 feet above the sea level. We climb 4,500 feet. You can see the terrain below us, the green, and around us. So if we increase the range like this, you will see more of terrain with green. You can see the engines also here, the center. So look to the flight plan here, better view across 6,000 feet. Also the head-up display. So we're gonna start the turn now. So we have the Zurich and the Switzerland, very beautiful view, the lakes. Over here we're gonna start the turn for the flight plan follow-up. So we have 18 more minutes for this flight, for the video actually, because I'm limited from my video time. So while taking this turn, again you look at the instruments, the airspeed is more than the stall speed here. Also the altitude is, rate of climb is positive. You can look up also the other side. Flight plan display also here on the right side. So we're gonna follow again, pitch down a little bit, maybe some flaps up. So flaps up now over here as we're climbing. So make a small turn here. As you can see, all indications are correct. The engines also, the autopilot flight director system panel here. So also the flight plan here we use. So let's look outside one more time. So we have a very, very beautiful view here. The Switzerland and the galaxies. The front side here, the Switzerland side here, and the Zurich, and the Switzerland, Swiss, and the lakes here. So the France again. So we'll make a follow-up of the flight plan over here, and we have 15 more minutes, I believe. Retract all the flaps here to increase the airspeed like this. So we need to follow also the flight plan. Make a small turn here. Maybe use some flaps until the airspeed is higher. So we have to follow the waypoints. The next one now, the nigger over here, as you can see the flight plan. So we're gonna make a small turn now, like this. So we have over here, need to follow, have a very nice crystal view now Need maybe to level up for a while. And we're gonna start the turn. So we need to pitch down a little bit to increase the airspeed, like that. So we're flying in the flight level 220 right now. So we have here the France, the Italy behind us, the Swiss Alps, the Switzerland, my homeland, the Germany in front of us, the Bayern Munich, with the beautiful lake here of the Switzerland, and also the galactic view over here of the Boeing 787. So we're gonna have also I believe gonna have the chemtrails in a while. So we have like 10 more minutes. So we have the Bayern Munich, the Germany, my homeland in front of you. The beautiful view. We have like maybe 10 minutes more. Over here, flying over the lake, very close to Germany, the Bayern Munich, very beautiful view. Then we're gonna turn. We have also the chemtrails now. As you can see, the vapors from the exhaust of the engines. So we need to start the turn now. Pitch down the aircraft slightly and start the turn here. So we have 10 more minutes left for this flight, like this with this turn. So we take a very sharp turn over Germany, my homeland, Bayern Munich over here. This is the way they fly in Germany, so hope you like it. So we keep him flying over here, use some rudder. You can see the right rudder for the right turn. And we have 9 minutes left for the flight to. So we need to level off a little bit over here as we fly. And we have 8 more minutes left for this flight. You can see, hope you like over here the view as we flying with my own hand fly. We have level off the aircraft at 27,400 feet. So we're gonna start descending also, decline manually. So maybe I'm gonna use the autopilot gonna give us a turn. So now we have connected the autopilot of the Boeing 787. Now we can disconnect like this, keep descending. So now we start the descent to the altitude block to the airport. Keep having the chemtrails here, as you can see. So we have about 7 more minutes left. So we descend again manually using my own controls over here. Disconnected all the autopilot. So we use idle thrust and maybe some pitch down now. And we have 6 more minutes left. So we have the maximum airspeed now on Mach terms 0.7. We're gonna use some increased rate of descent. So we have 5 more minutes left. So we have 5 more minutes. Actually we need to cross through these waypoints here. As you can see. So we're gonna make a small diversion here as we keep descending. And we'll have 4 more minutes. We need to start the turn to the runway. So we're gonna initiate the turn here. So we are here. We need also some flaps for landing, slow us down also, as we are approaching for the landing part. Now we have 3 more minutes, I believe, so we can fix also. The airspeed over here. So we need to advance the thrust levers a little bit more, and we have 3 more minutes left. You can see the Lszh localizer. We are very close actually to the runway as we are approaching. So we're gonna have also the outside view here. Advance the thrust levers a little bit more. So we need to increase the rate of descent for this approach and landing. So align with the runway, maybe for some side wing. Align with the runway. We're gonna have the flare in a couple of seconds. Speeds up a little bit for the flare, as you can see. So we're having here touchdown, very nice. Parking brakes and thrust reverse, idle thrust and thrust reverser here. So we are slowing down, full thrust reverse, 100, 90, 80, 70. So we're slowing down, as you can see, 40. So this is just landed in the runway. We still have some runway left. So we made a very beautiful landing over here, as you can see. All on the nose wheel here. The parts, the landing gear, you can see the nose wheel is standing up the way it should be. There is no breakage of any part, either the nose wheel or the landing gear behind it, or the tires. I don't know, the aircraft is standing up the way it should be. So that was Thomas Hatch's German American pilot flying the Boeing 787-900 tonight flight. Thank you for watching. I'll see you next flight. Bye bye. So you can see here, we disarm like this, the thrust reverse.